All right, I think we'll get this session started. Great to see you all this morning. This is the session on Visual Feedback 2. My name is Tobias Hollerer from the University of California, Santa Barbara. I'm going to be your session chair for 4 great presentations. We will have 1 presentation given online and then 3 in-person presentations. And so without further ado, I'd like to welcome Kelsey Quinn, who's going to talk about her and Joe Gabbard's work on augmented reality visualization techniques for attention guidance to out-of-view objects, a systematic review.
Hello and welcome to my presentation. My name is Kelsey Quinn and I work with Dr. Joe Gabbard in the Cogent Lab at Virginia Tech. Today I will be presenting on our paper titled Augmented Reality Visualization Techniques for Attention Guidance to Out-of-View Objects, a Systematic Review. So the increasing presence of AR in real-world scenarios, especially the expansion of AR as a hands-free tool in industrial and occupational settings, has afforded many benefits. But we also need to consider how to design AR interfaces so they help rather than hinder the performance of users. For example, we need to consider how we are going to present and convey task or goal-related information, while also considering available screen real estate and limited field of view in order to prevent visual clutter and occlusion, which may lead to unneeded distractions or decreases in performance. Therefore, in our research, we are interested in how to effectively design and assess AR visualization techniques to cue objects located outside a user's field of view and guide attention without increasing cognitive demands. We conducted a systematic literature review on existing AR visualization techniques and explored 3 different databases using combinations of search terms such as augmented reality, mixed reality, attention guiding, cueing, out of view, and other combinations of these terms, which are all detailed in our paper. We followed the Prisma flow model, and specifically within the eligibility stage, we applied a set of exclusion criteria, which include VR papers, papers that use mobile AR, non-visual cueing modalities, papers that guide attention to objects inside the field of view, and papers that were not full text accessible. The justifications for our exclusion criteria are further explained in our paper if you are interested in learning more. Once our final refinement was complete, we included 37 total documents into our review. This figure here shows the outcome of our systematic review. So we identified 19 different techniques, which were all created with the intention to guide a user's attention to an object outside their field of view. So the other 4 of the 19 techniques are not shown here because they combine 2 or more techniques in temporal ways. Some of these techniques were created for AR and others were initially created for other digital systems and then subsequently adapted to AR. However, all techniques were studied using a head-worn display, head-up display in either optical see-through AR, video with pass-through AR, or AR simulated in VR. We also can see that some of these techniques are egocentric, such as image letter I here, the 2D arrow, and some techniques are exocentric, such as image letter K here, the IC360. We will discuss these approaches to visualization techniques in a few slides from now. And sticking with the theme of reducing visual clutter, the full citations for these images can be found at the end of our presentation. For each paper, we recorded a set of dimensions, which were all related to the design of the visualization techniques, how they were studied, tasks, and associated user measures. Given that we have a short period of time, we will focus on pre-attentive visual properties, information encoded, specifically direction and distance, assessment measures, and study results. So one of the dimensions we recorded includes pre-attentive visual properties, which were established by Colin Ware. In visualization techniques, pre-attentive properties were leveraged to encode information about out-of-view objects, specifically information regarding distance and direction. So in AR, users must visually attend to real-world events and objects of importance, as well as the virtual information, creating a divided attention scenario. And when we consider that human visual attention has limited capacity, these properties allowed for detection within the visual field before users intentionally focused their attention. The first pre-attentive property is color, which is shown here. First, color is utilized, for example, to encode direction in the 3D radar. So the color of these circles, either blue or white, are indicating if the object is located in front of or behind the user. We also see color being used to encode distance, for example, in IC360, following the warm, cold gradient, color gradient. So blue and red color of proxy icons to indicate how close the user is to the object. The second pre-attentive property we saw leverage was form. Specifically in the wedge technique, collinearity was used, so the sides of the triangles, of course, ended in a point of the triangle, which then located the location of the out-of-view object in order to encode direction. We also see form being used in 2D arrow, so the size of the arrows corresponds to the distance the object is relative to the user. The third pre-attentive property is movement. We see movement encoding both direction and distance in Dyne's wave. So these animated waves seen in Dyne's wave are going in the direction of the out-of-view object, and the speed of the waves is indicating how close the user is to the object. The final pre-attentive property is spatial positioning. This was leveraged to encode direction in top-down bird's eye, just as one example. So we see the use of a proxy icon for the out-of-view object and a proxy icon for the car that the user is in. And so the location of the proxy relative to the car is indicating the direction of the object. We also see spatial positioning encoding distance in 3D radar. So the placement of these proxy icons within or on these rings indicates the distance the object is relative to the user. This table here summarizes how each technique in our review encodes direction and distance of out-of-view objects. So there's lots of information that techniques could encode. For example, if the out-of-view object in the environment is a hazard, the AR visualization technique could encode the type of hazard or the level of danger of the hazard. We found that most of the techniques in our review focused on encoding direction and distance, most likely to inform the location of objects relative to the user. And so we can see here that, interestingly, spatial positioning was frequently used to encode direction, but we see that color was not frequently used to encode direction, which may suggest that color is reserved to encode a different piece of information. We also explored dependent measures frequently recorded and created this comprehensive summary of the performance of each technique in relation to others. So tasks commonly completed within these studies included out-of-view object collection, search, and position estimation. We see the top here along the top of the table is indicating the common assessment measures, and the first column is listing out the visualization techniques. So a check mark is placed in a cell on the table if that is the most effective technique for the given measure. We see a black filled-in circle to indicate that the measure was studied, but that technique was not the most effective. Cells that contain both a check mark and a black filled-in dot are indicating that there are mixed results across studies, and empty cells are denoting that, to the best of our knowledge, that measurement has not been recorded for that technique. You can refer to our paper to see what techniques were compared against one another if you're interested in more details. An interesting finding from this table includes the underrepresentation of location accuracy being recorded in studies, especially given the fact that mitigating error of direction and distance of out-of-view objects is important to consider when we're designing cues. Some key takeaways from our findings from our review. The first is the amount of information on the technique. For example, this might differ between a novice versus an expert. So some users may be able to decide what information to focus on because they may no longer need all the information once they are familiar with the visualization technique. A question that goes alongside this is if there's a threshold for the amount of information that significantly increases cognitive and visual clutter. Another interesting takeaway is the need to consider the use case of applications of these visualization techniques. For example, using exocentric versus egocentric techniques. So exocentric techniques provide information about the location of an object relative to the user and other objects in the environment, which can be important during a task that requires high situation awareness in order for the user to gather context. But exocentric also requires additional mental effort because it requires the user to transform the map view to the user's first-person view, which might not be ideal during the completion of tasks that already require high cognitive demand or divided attention, such as emergency response. In such use case, egocentric might be the better approach, since egocentric techniques display an object's location relative to the body axis or field of view of the user, therefore affording the direct first-person view of an object's location. Another takeaway is the consideration if the user is completing both a primary and secondary task. We can see in this image here, this is the use of a visualization technique to guide the user to objects related to a maintenance and repair task. If this is the primary task of the user, is this repair? Let's say the secondary task is possibly monitoring other machines in the room. We need to make sure that we're managing the user's attention so they can complete both tasks efficiently, and we also need to consider the design of the technique so it is not distracting the user from the secondary task. Future research includes exploring these techniques in large-scale outdoor environments or field-based settings. So the techniques we reviewed were studied in either laboratory or controlled settings. We also discovered that all the techniques were studied queuing to static out-of-view objects. So future research could be evaluating these techniques for moving out-of-view objects. Another gap in the research is how these techniques may queue to more than 5 out-of-view objects. So all of the techniques, with the exception of one, queue to 5 or less out-of-view objects. And so if we increase the number of objects in the environment, we might get a better understanding of how well these visualization techniques scale to larger object sets. And finally, interestingly, but not to our surprise, we discovered that most studies only queued virtual objects rather than real-world objects. We think the most probable explanation is that it's logistically easier to queue to and study virtual objects, since both researchers and testbed software can easily know where virtual objects are in the environment relative to users. So future research may include queuing to real-world objects instead of virtual. Thank you.
All right, thank you, Kelsey. Are there any questions for Kelsey? While you're thinking about them, I can get it started. Can we get her on the screen by any chance? No? Okay. So can you clarify the inclusion-exclusion conditions for me a little bit? So I read in the paper that you excluded the term mobile AR, but you more meant with that like phone and tablet form factors, I think. But then on your last slide, you also had that you're not covering here outdoor environments and larger spaces. It seems like that these techniques are especially desirable in these spaces. So I would love to hear your comments about like why you decided to exclude that.
Sure, so we decided to exclude mobile AR, which we defined as AR delivered via phone or tablet, independent of whether or not the user was moving. This is because most of the techniques were studied using head-up displays, as well as we were including the fact that there's a narrow field of view of AR displays, and that was one of our scopes of our work. But I think that the introduction of these techniques into larger environments would be a great research next step, which is what we're hoping to complete in our next research, is seeing how these techniques can perform in larger scale environments with multiple objects in order to further the research here.
Thank you. But just to like understand, were studies with larger environments included in your paper collection or not at this time?
No, not at this time. Most of the studies were conducted in a laboratory or field-based environment, or sorry, laboratory or controlled environment. But after the time frame of the completion of this review, we have discovered some techniques that were completed in larger scale environments, such as the compass that you worked on with your team as well.
That is not why I asked the question, but I was really interested because it is, I think, a really useful summary for the big field of moving AR users. I think we have another question.
Yeah, hi. So first, great research, very interesting and very useful for community. It's very similar to research I presented yesterday about similar UI for guidance. Anyway, I'm question for you. So what we can from our study is also the missing of a standard in evaluating those interfaces. Do you think that could be created a kind of common framework to compare one-to-one those interfaces and from a quantitative point of view? Thanks.
Thank you for the question. Yes, I think that would be very helpful, especially considering that a lot of work has not explored the different types of information or, for example, pre-attentive properties that have been used, which might be included in this sort of systematic evaluation of the technique. And I think that through a systematic evaluation, we can better determine what design elements or design characteristics should be continued for use in future techniques.
So in short, also, there are every of these paper you presented have a different way of comparing, or you can find a kind of pattern in that. So maybe this is another question similar.
Oh, good question. So the way we completed that comparison table that was shown on one of the slides was some techniques were compared to others just in terms of performance measures. And so not all measures were recorded in all studies, which may help in the future to accurately compare all techniques across each other.
Thank you.
Great. Is there another question? Okay. That doesn't seem to be the case. Thank you for the great presentation, Kelsey. And we go on to EXA prototyping of mixed reality visualizations, compensating interaction latency for a medical imaging robot. And the presentation is going to be given by Hendrik Plümer. And his co-authors are Kevin Ulrich, Denis Kalkofen, Philipp Steininger, Nassir Navab und Markus Tatzgern.
Yeah, hi. My name is Hendrik Plümer, and I'm going to present our paper on behalf of all authors. This means I'm going to talk about extended reality prototyping, why it is beneficial for us as researchers, and how to conduct a study with such a prototype. I will also explain our interaction latency use case to you. Recent years have seen a surge of interest in using mixed reality for medical applications, such as 3D medical teleconsultation, data visualization for surgical planning, or other forms of assistance during medical procedures. This includes medical robots and their potential for new augmentations. For example, this robot over here, this is the Loop X, a mobile cone beam CT robot used for image-guided medical procedures. It creates images like this to aid the medical staff with their treatment. And one advantage of the Loop X is its driving capability, as operators can move it with a remote control if needed. And this allows a more flexible utilization. Unfortunately, this also introduces perceivable latency caused by the robot's way of operation. Imagine this. You're driving forward, which means all wheels or four wheels are aligned straight ahead to enable this forward movement. Now, if you want to drive to the right, the robot stops its forwards movement and starts turning the wheels to the right. And after they are turned, the robot starts moving to the right. So during this wheel alignment phase, it is easy to perceive the robot as not doing something because you cannot see the wheels actually turning. This is what we want to improve on. We will enhance the Loop X with mixed reality visualizations to counteract the perception of latency. And to give you an impression of what it looks like, this is our baseline or direct control condition. And as you cannot see, after the rotation of the robot stops, the wheels align themselves for the following sideways movement. Maybe it will be clearer here with our first visualization, steering. The white lines represent the current orientation of each wheel. Now, in previously as inactive perceived situations, you can indeed see that the robot is still active. You can think of it as some sort of loading indicator or progress bar. To circumvent the visualization of waiting times altogether, an alternative is using some form of a surrogate. In our case, we built a see-through virtual copy of the robot, which is controlled instead. And this copy will generate waypoints for the original robot to follow along on its own pace, so that in the end, both robots will drive the exact same path. The surrogate is not restricted by inertia or waiting times when turning the wheels, which should result in a more pleasant user experience as changes in directions are immediately realized. So now that we have defined these three conditions, they can be compared against each other to answer our first research question. Do our supporting visualizations help to mitigate the perceived latency of the robot, and which one is the preferred one? Before we investigate this further, though, we need to talk about potential obstacles one may face when conducting such studies, as these types of robots are rarely available and costly to acquire, and access to them or your study space might be restricted due to regulations to maintain patient and operator safety. You may ask yourself, how do we circumvent these obstacles? And this is what extended reality prototyping, or XRP in short, is for. Because instead of utilizing the real product, you build a simulation of it to use instead. And with an XR prototype, all those previously mentioned obstacles of price, availability, and restrictions would no longer exist. Moreover, XRP would not only benefit research, but also the industry, as companies could postpone the development of physical products and thus save time, material, and money. So to test this, we built an XR prototype for the three conditions as well. This is the direct control condition. Users steered a virtual copy of the original robot. And as you can see, the perceivable latency between changes in direction is given here as well. And you may have also noticed the real robot in the background. It is standing there at its parking position and not part of the XR condition themselves. This is our steering condition. Here you can see the XR prototype, but with the white lines to showcase the rear rotation. And this is our XRP surrogate condition. Here you now have two virtual robots. The surrogate you control, just as before, without inertia or waiting times, and the trailing prototype. With these additional three conditions, we not only collect more data for research question number 1, but we are also able to directly compare our prototype with its original version to answer another research question. Are the XR prototype and its original counterpart equal? And can we transfer results gathered in the simulation to the real world? If this would be the case, we could reliably use the XR prototype even in the early stages of product development without the actual physical product. So now that we have defined our conditions and research questions, we can conduct the study. 24 participants volunteered with an average age of 25. Half of them were female and the rest were male. They each had to perform all three visualization conditions, direct control, steering, and surrogate twice, once with the original robot and once with the prototype, so participants performed the task 6 times in total. A typical task looked like this. Starting from the parking position, they had to maneuver the robot towards the table and align it with the target. We measured task completion time, task load, and usability, requested participants' preferences, and interviewed them at the end. Now, do our supporting visualizations help to mitigate the perceived latency of the robot? Yes, they do. With the surrogate condition, for example, participants were significantly faster than during the other two, which we expected as the surrogate was not restricted by inertia or waiting times when turning the wheels. In terms of preference, any kind of latency visualization was considered helpful. The steering condition was already much preferred compared to the baseline, with the surrogate scoring slightly better results. Users significantly disliked the direct control condition in comparison. The question whether the XR prototype and the real-world counterpart are equal is relatively clear to answer, as unfortunately, even though we tried our best, they are not equal. If you look at task completion time or the task load, for example, the prototype performed significantly better. Participants were significantly less stressed with a lower mental demand, which, according to feedback, might be justified with the perceived risk of steering the real robot. So in contrast to the virtual prototype, you could theoretically drive into obstacles and potentially damage it. The good news is that even though they are not equal, results can still be transferred, as we found equal relative effects. For example, in research question 1, we showed that the surrogate condition was significantly faster. And if we investigate this finding on the per condition basis, you can see that it still holds true. Both surrogate conditions were significantly faster than their respective other conditions, and this observation also applies to the remaining data as well. So, what knowledge did we gain from our work? First, visualizing processes improves responsiveness. This is already true if it's only a visualization, which does not improve the actual speed of operation. User feedback indicates that the type of visualization we have chosen requires improvement, but visualization is clearly beneficial compared to no visualization. And if you can mitigate the actual latency as well, for example with a surrogate, that's even better. Secondly, even though we were unable to prove equality or absolute validity, we still provide new knowledge to the research of XRP validation studies by reaching relative validity. And what does this mean? So ideally, your prototype and its real-world counterpart behave and perform identical to each other. Let's say you found some sort of effect, for example, this sort of ranking of conditions where A is smaller B is smaller C. When investigating your conditions for the real-world robot. If you can statistically prove the same effect with equal performance for your prototype, you reached absolute validity. This is great, as you should be able to only use the prototype for all upcoming work without requiring a physical product. Fortunately, even if your simulation is not a perfect match and there are performance differences to the real world, you can still search for equal relative effects to reach relative validity. This still enables you to make statements about the product or its variance without access to it, which includes changes early in the development process. We carefully designed our study to enable us to prove relative validity by using a generally applicable framework from previous work. And for more details on that and on these types of studies, I suggest you read our paper. Where are we headed next? Despite our careful study design, simulation and real product were still different from each other. This is likely caused by differences between simulation and real product, but it may also have been caused by additional use case specific factors, such as the participant's sense of agency in this case. Sense of agency describes the feeling of control I have over my own actions and therefore over changes in my environment. We noticed this potential influence, especially during the surrogate condition, where users only indirectly control the actual robot through the surrogate. Participants reported differences in feelings of safety and comfort, as apparently our prototype was not as stressful. So if this indeed caused the differences between our prototype and the original robot, it provides further potential for additional improvements of XR prototypes, because if we can identify the source of these insecurities, we could include it into the construction of the prototype. And this would enable us to recreate the same psychological aspects of the normal user experience for the XR experience. It would be a big step towards reaching absolute validity and therefore towards an overall benefit for XRP validation studies. This concludes my talk. If you are interested in our work, you can find a version of our paper when scanning this QR code. Thank you.
Thank you, Hendrik, and let me start the questions by congratulating you on the Honorable Mention Award as announced yesterday at the banquet. So, are there questions? Yes.
Okay. First, thank you for a very interesting and practical paper. I have a question about the surrogate model. Since it's not, as you said, it's indirect form of movement for the machine. Is there any potential dangers or like reported user response over the gap between actual movement and control? Because since this is a lab-based like experimental setup, there's not much of dynamics in the environment, but if the real patients are there or other people are there, there might be some environmental changes during the movement, and between the time gap might cause any problem. I'm just curious.
Yeah, that's actually a very good point. So our, let's call it following algorithm was kind of stupid. So we just generated waypoints with the surrogate, and the real robot followed. And for example, if you made a mistake with the surrogate, the same mistake would have been made by the following robot. And this was actually a point the participants remarked upon. This is likely the cause of these insecurities we noticed, because you can't really control the following robot. There would be, future work would need to improve on this following algorithm, for example, by security measures like, I don't know, we thought about some collision detection or something which would then stop the robot or something like that. But yes, this was actually a point of interest, so to say.
Thank you. We have time for one more question.
Hi, Alejandro Martin, University of Arkansas. Really interesting. It's definitely something we could use. I just have a specific question where you show your surrogates. It goes more on the subjective aspects. Did you receive any sort of feedback in terms of like visual overload, particularly when you have your real robot and the two surrogates?
Yes, so interestingly enough, some users reported on not being able to distinguish between the robots, which is actually kind of good for us, because that showed, okay, we did such a good job of visually recreating the robot that it was hard to distinguish the real one. But yes, especially in the surrogate condition, the presence of 3 robots, even though only 2 were active, was for some users a bit overwhelming. Yes, indeed. Yeah, and they remarked upon and criticized this. Yeah.
All right, let's thank Jan Hendrik again. And we go on to the third paper presentation, Optimizing In-Contact Force Planning in Robotic Ultrasound with Augmented Reality Visualization Techniques. The authors of this paper are Tianyu Song, Ulrich and Nassir Navab. And Tianyu is giving the presentation.
Good morning. My name is Tianyu from Technical University of Munich, and I will be presenting our work on optimizing in-contact force planning in robotic ultrasound with augmented reality visualization techniques. So our goal is to enhance the safety and transparency of the robotic ultrasound. Thanks. Our goal is to enhance the safety and transparency of robotic ultrasound by providing intuitive and efficient AR visualization force feedback. So robotic ultrasound poses several challenges because robots directly interact with the patient and making it very difficult to control force in real time. And this is also very critical to obtain a high quality image while ensuring patient's comfort. On one hand, patient must accept the system for it to be widely adopted. Imagine if you're the person in this video and you see this robot coming towards you, wouldn't you feel a little bit nervous? Especially if you have worked with robotics before and you know how things can terribly go wrong just in a second. And on the other hand, the doctors also need to trust the system to be widely adopted. So they need to trust the system that it will correctly do this job. So in this work, we focus on the doctors or the practitioner side of the robotic ultrasound. And you can think of this like self-driving car performs a parking. And if you see the planned trajectory being visualized on the screen, and this gives you more confidence to trust the system and let the car park itself. Similarly, in this work, we aim to provide a better AI feedback mechanism to optimizing contact force planning during robotic ultrasound. So in the ultrasound procedure, it requires precise force control to ensure optimal contact between the probe and the patient's body. Insufficient force lead to poor image quality, while excessive force causes discomfort or even harm to the patient. This is particularly challenging in robotic ultrasound, where there's no direct human touch. So we need to come up with like an alternative method to plan, monitor, and adjust the applied force. And augmented reality can help bridge this gap by providing visual feedback on the force planning without relying on tactile sensation. So if we take a look at how force is currently being visualized in the field of robotics, we can identify several common categories. So for example, in some systems, the value of the force is directly labeled in text, such as this robot weaver presented by Hu Lin. Or the most familiar method when we learn physics, using an arrow to represent force. As an example, Suarez implemented a method that displays contact forces applied by robotic hand's finger using arrow visualization. And recently, in a mixed reality system for remote ultrasound presented by Black, color was used to indicate when the remote sonographer should apply less or more force during teleoperation. And lastly, Harwick's work conducted a comparative study of different visualization techniques in robotic simulations, including arrow along the robot trajectory, and line charts, bar charts in a separate graphical user interface. And their findings highlight the vector arrows were particularly effective compared to like the chart methods, demonstrating improved user interaction with robot control. And in this context, it becomes very crucial to identifying the most effective and intuitive ways to implement such visualization in AR. And based on these insights, we design our AR visualizations to focus on augmenting the robot or the environment directly. So before I introduce the proposed force visualizations, let's first establish the baseline method we're comparing them with, which is representing force as a vector arrow. So this is a commonly used approach in many applications where the length and the direction of the arrow indicate the magnitude and the direction of the force. We also integrate the color coding into the visualization as well, where blue means insufficient force and green indicates the force is within the optimal range, and red warns the force is excessive. So the first proposed visualization is called squeezable arrow. As the name suggested, this technique augments a deformable arrow inside the ultrasound probe, with the tip of the arrow positioned at the midpoint of the probe contact area with the patient. Unlike the traditional vector arrow, which typically extend from the contact point into the body, a squeezable arrow's visual anchor is reversed. It ends at the probe's contact point. This mimics the natural human's sensory feedback, where the pressure is actually felt at the source rather than perceived as extending inward. As the probe controlled by the robot apply more force, the arrow visually compresses or squeezes downwards, simulating the behavior of a real-world deformable object under pressure. The next AR visualization technique, named linear gauge, usually represent force application using a concept similar to like a water in a filling up a container. This visualization is augmented directly onto the ultrasound probe. As the force increases, a color field rises from the bottom of the probe, mimicking the behavior of water filling up a container. And on the other hand, as the force decreases, the color level lowers. Additionally, to display the force along the trajectory, a duplicate of the probe with the active visualization can be spawned at each of the control points. And two outline markers are placed on the probe as well, and these markers define the upper and lower limits of the optimal force. And lastly, we propose a force heat map visualization. This enables direct augmentation on the patient body itself, which not only provides instant feedback on the force application, but also contextualize it within the anatomical structure, enhancing spatial awareness. It adopts a color-coded circle directly augmented onto the patient's body. The size of the circle varies dynamically with the force applied. As the force increases, the circle expands, and as it decreases, the circle gets smaller. And this can effectively create a brushstroke along the path of the probe, so which can provide a visual history of the force applied during the procedure. Two additional circle outlines are also provided around the primary force circle. This outline defines the boundaries of the optimal force range as well. So we hypothesized the following. First, the squeezable arrow will have similar task completion time to the vector arrow, but would offer a better usability. Second, the linear gauge and force heat map will outperform the vector arrow in both task completion time and usability due to their direct intuitive feedback, but also with the visual boundary in these visualizations. Third, the force heat map will reduce cognitive load because environmental augmentation provide a more holistic view of the operational context, potentially making it easier for the users. To test these visualizations, we conducted a user study with 20 participants aged between age 29.6 on average. We equipped them with a HoloLens 2 and a virtual universal robot UR5 aligned with the real robot, which represent the planning of the robot's force and motion, and an Xbox controller for interaction. The independent variable in the user study was the visualization technique, and we measure several objective and subjective dependent variables, including task completion time, force consistency, workload, usability, ease of use, preference, and feedback. The tasks each user needs to do involve three specific steps. First, identifying and marking the points where the planned applied force was either below or above the optimal range, which was set to 5 Newton to 10 Newton. Second, adjust the force at these marked points. And third, replan and verify these adjustments. And at these steps, the user can still go back to the step 1 if they want to. In terms of objective measurements, we found that all visualization provide a similar force consistency. However, linear gauge significantly outperform all other visualization techniques in task completion time, allowing users to complete the task faster while maintaining accurate force control. From the subjective measurements, we found that the linear gauge and force heat map scored the highest in terms of usability, ease of use, and preference. The vector arrow was the least preferred method, actually. And from the feedback, the linear gauge visualization was praised for its simplicity, particularly because of this one-dimensional scale featuring clear and upper-lower boundaries. And our results showed that the squeezable arrow had a comparable completion time to the vector arrow, but did not improve usability, and users expect a direct correlation between increasing force and a large visual cues. Second, the linear gauge and force heat map outperformed the vector arrow in both objective and subjective measures. And third, the force heat map showed a trend of lower cognitive load, but there's no significance. This is because the body's curved and deformable surface adds to the complexity, where some participants need to adjust their viewing angles. So one key insight from our user study is the effectiveness of the simple design principles in AR visualizations. The design of a good AR visualization technique needs to be balanced with the understanding of cognitive load and user psychology to ensure they actually enhance rather than hinder the user experience. The challenges with the squeezable arrow provide valuable lessons for us. In addition, utilizing the robot tool itself as the canvas for displaying contact force or relevant information has been shown to enhance user interaction and comprehension. By augmenting the directly onto the robot or tool, we can utilize existing physical marker or natural features as the threshold indicators without additional visual clutters, and incorporating clear bounds or threshold indicators within the visualization provide precise references that are essential for fine control. And for future work, integrating sonification with visual cues offers a promising direction. In conclusion, the linear gauge and force heat map visualization were the most effective at providing simple, clear feedback for force planning in robotic ultrasound. This technique provides improved usability, reduced cognitive load, and made it easier for clinicians to apply correct amount of force. And the study highlights the potential of AR to enhance human-robot interaction in medical settings, improving both accuracy of the procedure and doctors' trust of the robotic systems. And the work is funded by Phonero project. The author would like to thank all NARIS and IFL lab members for their valuable feedback. And our code is also publicly available. Thank you.
Thank you, Tianyu. We have time for a quick question. Yes.
Thank you for the presentation. It's a very interesting one. This is Yemi from Duke University. So my question is, how did you define the boundary between the insufficient force, optimal force, and excessive force?
Yeah, so based on like the, where you do the scanning of the robotic ultrasound, there's already some literature that defines the optimal force range. So in this user study, we look into those literatures and found out that like between 5 Newton to 10 Newton is optimal for like abdominal scanning. So for different areas, like for example, spine has a different force range as well. So you can definitely define this by yourself beforehand.
Yeah, thank you.
And maybe the next and last presenter can set up while we maybe ask Tianyu another question.
Can I have a quick question? Is like individual difference of like body tenderness or like patient moving while procedure can be applied directly toward those kind of force range and things?
Sorry, can you repeat?
Okay. What I mean is that they could be the movement of the patient during the procedure, or like individual has some difference in body thickness or like skin thickness. Is that can be individualized or like visualized?
So like in terms of robotic ultrasound, like some of the robot has like force sensor itself, so it can measure the force. So like especially in robotic ultrasound, I only care about like the force that is applied in the vertically, and we only cares about like the magnitude of the force in this regard. So for like skin thickness, was not considered in this user study. Yeah.
Thank you.
All right. I think we have the next talk lined up. Thank you, Tianyu. All right, so the last talk of the session is entitled Enhancing Human Task Performance Through Audiovisual Augmentation. The authors are Tobias Schwandt, Gunjan Kumari, and Georg Stolz, Stefan Werner, and Wolfgang Broll.
That's right. So if we're talking about augmented reality, we're usually thinking about adding visuals to our current view that we have. And of course, in addition to only visuals, we could also add different things, like also audio. And the question of the study that I would like to present today is how audio-visual augmentations, so both of it, can enhance human task performance. This is part of a project funded by the European Space Agency. And a part of the project was Gunjan Kumari, Georg Stolz, Stefan Werner, Wolfgang Broll, and me, myself, Tobias Schwandt. And today I would like to show you what we have investigated on in the project and what the results was, because this is actually the part of the study. So, as an introduction, The question that we had during the project was how we can, or in space environments, so especially if you have maintenance tasks there, you always have the problem that you have a high workload and the task performance needs to be correct. And of course, you have in space in general limited sensory perception. And the question was if we can improve that by adding audiovisual augmentations to improve that task performance. And additionally, we also ask if we can enhance situational awareness and also workload. And therefore, in that study, or in the project, we simulated a maintenance task aboard the International Space Station. And we did all of that in virtual reality. But the question actually is more about augmented reality, so the augmentation of that. The VR part was just our tool to being in space in that particular case here. So the problem statement was that with impaired perception in environments like space, for example, that lead to slower task performance, higher workload, and reduced awareness. But by incorporating visual, audio, and combined visual cues, we can improve that. So at the end, we had the research question of what is the influence of audiovisual augmentations on maintenance tasks in unusual environments. So we made it a little bit broader, not only space. And therefore, we had 4 different hypotheses. Audiovisual augmentations improve workload. Hypothesis 2, audiovisual augmentations enhance situational awareness. Hypothesis 3, audiovisual augmentations lead to faster task completion. And last but not least, lower workload correlates with faster task completions. So to answer these research questions and to evaluate these hypotheses, we had a study design which looks like that here on the right side. So we had the ISS simulation with our maintenance task. I will also have a short video for you which demonstrates that a little bit more clearer what is going on. Just for the facts, we had 43 participants and most of them had a STEM background. The mean age was 30 years. And 31 was identified as male and 12 as female. The task in that situation was that you have to identify and deactivate a male functioning pump, and therefore you had to use a control panel. To tackle our research question and the hypothesis, we had 4 different conditions. We had no cues at all, which was at least just the VR simulation, so without any audio because you are in space. Then we had audio augmentations, then we had visual augmentations, and audio-visual augmentations. As I said, I have a video for you to show you how that looks like.
So performed maintenance tasks with cues.
So here we are. At the beginning, the participant was just put into the scene where you are attached to a robot arm next to the ISS. And there was some acclimatization task at the beginning where you just can take a look around, get comfortable with the environment. And after a while, you get, unfortunately, we haven't heard that right now, there was some radio command. And the radio command just gives you just the instruction of what to do. So there's a male functioning pump, and we will bring you there, and you have to solve the issue that we have. The robot arm is very, very slow, so that's why we fast forward that here a little bit, because we would like to reduce the motion sickness. So, and then you have arrived at the control panel. And now you get a radio command where you, unfortunately we cannot hear it, I don't know, there's some error with the audio somehow, but the radio command says, yeah, there's a male functioning pump, you have to identify which one it is, and to solve the issue, you have to reduce the power level of the male functioning pump and compensate that by enhancing the power of the other one. So it's actually a very simple task, but as you can see here, this is the audio-visual cues that you have. So we have audio, we can hear the pumps. Some of the pumps are working very nicely, so you have a nice sound of the pumps. And one of the pumps was making some crackling noise, so it was very clear, okay, this one is not working. And then you can, with the knobs, you can rotate these and increase or decrease the power. And if you have done that by doing so, you have to click the button, and then the task was over to check if everything was working. Now here you can hear maybe a little bit the male functioning pump, like some gives a noise, and then you for that and clicking OK, and then task is over. All right.
DR simulate.
Sorry. So for the study design, we had a pre-questionnaire, of course, to ask some demographic questions. Then we had identified a user ID, depending on the condition that you got. We run the study, and then we had a post-questionnaire where we asked different questions to tackle our hypotheses. So we had NASA TLX, situational awareness questionnaire, and some others. Before we get to the results, I would like to just talk a little bit about the setup that we had. As you may have seen, we had that VR simulation, and we are standing in front of a control panel. And the control panel in the virtual world, we had the same also in the real world. So we had a digital clone of a real control panel. We did that to have a tangible interface for our environment. So everything was tracked with using OptiTrack system. So, and when you was moving, for example, the lever of the control panel, that has a direct influence also on the virtual world, just to have some kind of haptic here inside. So that was the main reason about that. It was at the end a combination of that digital, of that real world control panel together with an HTC Vive Pro. And everything was implemented in Unity using spatial audio. And we have used the MetaXR audio SDK for our purposes. All the rest is used NASA 3D assets, which is actually available on GitHub. So if you ever have to do something with a space environment and simulate that, NASA and also ESA providing very good assets for that. So we had that realistic, somehow realistic ISS simulation with these not so realistic pump task. We identified, or we had a long discussion with ESA what we can do, and that was the one that was more or less something that could be useful for them as an output. And now let's check the results. So we had, as I said, 43 participants, and each of the participants get a different queue. And we have seen that people with getting audiovisual augmentations are significantly faster as people who get no cues at all. But they're also a little bit faster than people with having only audio. So, and people with audiovisual are also better than having just visual. So audio improves here a lot, or the combination of audio and visual improves here a lot regarding task completion. The same for, or not the same, but for workload, so NASA TLX workload, we can see also that we have some kind of decreasing, so you can see that it has somehow an impact, but it's not significant here in that case. Another interesting result may be, well, it's a custom question that we ask in addition to all the standard questionnaires. We ask how easily were you able to distinguish which pump was broken. And on a 7-point Likert scale from very difficult to very easy, they said they have with audio-visual augmentation. It was definitely much easier instead of having none, of course, right? Besides that, here in the upper right corner, you can see a QR code. So if you're interested in more information, this will lead to some supplemental material. The same supplemental material is also in the paper. There you get more plots, more evaluations, and also the source code and everything that you might be interested in, just for you as an information. Okay, let's come to a discussion. So we have seen that audiovisual cues offer a very efficient way or a possible way to improve task performance, especially in situations where you have limited perception. As I said, in space we had no audio, only the radio commands, and that's it. So we have seen that we have here somehow an improvement. But of course we have to also check what kind of limitations that we have. The biggest limitation most probably is the not simulated microgravity. It's very hard to do that here in the real world, to simulate microgravity. We had a discussion with ESA and they said, yeah, maybe you can do a parabolic flight. But during that 1 year of project time, that was not possible to do that. But we are still in discussion with them if we do that further. So that's one of the future tasks that we would like to do, to really test that microgravity and also test that with real world experts. Because the participants that we had a STEM background, so they was used to have VR. They know what VR is, because we don't want to have someone who's novice in this case to just having not the problem of what's VR, and they're so overwhelmed about that. So, but they're not experts in the sense of that they're really astronauts. So as a conclusion, maybe the takeaway for you, if you're thinking about adding visual stuff, visual augmentations to your application, please also think about audio. I saw in the presentations before that there are still some things, the presentation before actually had in a future work, yeah, we could also add audio. Yeah, why not? It makes a lot of sense, right? Because it really helps to get people, or to help people with doing stuff, maintenance task, whatever. So as a future work, just to sum up, we need to test that with experts, for example, astronauts. But another way would also be to get rid of the space environment and maybe go with another environment, like underwater or underground experiences, where you also have somehow some kind of limited perception to see if this audiovisual augmentations could also help here. Okay, time is running. I would like to thank you for the attention. If you have any questions, now we have some time a little bit, right, to ask questions. If you have some questions after that, you can use either Discord, or you can also reach out to us. Here's my mail address, and the QR code actually leads to our team website, where you have also the contact possibilities with everyone in the project. Thanks.
Thank you, Tobias. Let me kick off the questions, maybe. So it seems to me that the value of audiovisual feedback depends a lot about the mapping from sensed data to that visualization or realization. Especially if you have a maintenance task where you have to figure out if something is broken. But I mean, if you'd have to design the mapping, wouldn't you already need to know that something is broken in order to design a like working mapping that actually gives you like good results?
Yeah, that's totally true. That's actually one of the questions that we also had with the visuals. So if we know what pump is broken, we already see that, right?
Right.
So
you could just point to it, right?
Yeah,
give direct advice.
That's totally right. So that's why maybe that's why we had in the future work, it would be maybe also interesting to go into other directions and other tasks which are maybe underwater or underground, which maybe makes more sense in that case. It was just in discussion with ESA that was one of the, which is most closely to something that they did if they're getting in outer space and had to do something in maintenance tasks. But yeah, you're totally right. Yeah.
Are there questions? Yes.
Ulrich, TU Munich, thanks for the talk. You're studying it in situations with limited perception, right?
Yes, right.
Do you think your insights would also translate to normal situations where the perception is not limited?
Yeah, that's right. In the related work, we found out that in situations where you have no limited perception, like in space or somewhere, it already leads to having better task completion with audiovisual. So the question here for that project was particular, especially for unusual environments.
Okay, thanks.
You're welcome.
Thanks a lot. I'm really interested, as you know, on this subject. Do you think we can come up with, better evaluation? Because we always have this problem that they are used to something, and now we give them something new. So I'm not sure if always time and accuracy would be enough evaluation methodology. Do you have any idea of how we can do other evaluations that would allow us to see the, in short term, before they do the training and learning the new, how to take advantage of this new environment? Do you have any idea how we could improve this evaluation in general, make it more quantitative?
That's actually a very good question. Yeah, that's something I may need to think about in the next days. Very difficult to answer it right now. Of course, there's a high need to have a better evaluation here in that case, because it really lacks regarding, in this special case here with the study, that we have not the astronauts, that we had VR. So of course, the closer we get to the real environment, the better it would be. But yeah, besides that, difficult, right? Very difficult, sorry.
Okay.
All right, it seems like that was the last question, and that does conclude the session. So everyone enjoy the break, half an hour, and then we have the next set of sessions.
Thanks a lot.